Welcome to Design World's How to Calculate series, where you learn how to apply the most important equations for sizing, selecting, and comparing linear motion and motion control products. In this session, sponsored by Electrocraft, we'll learn how to calculate the output power of an electric motor based on speed and torque. In motion control applications, motors are typically chosen based on their torque and speed capabilities, using a torque speed curve that shows the motor's performance when paired with a specific type of drive and operated under specific conditions. But motors can also be rated or specified by their output power. But before we discuss power, we need to define work. Work is force applied over a distance. It's expressed in units of joules, where 1 joule equals 1 Newton meter, or in units of pound-feet. Although work and torque have the same units, Newton meters or pound-foot, work is a scalar quantity, meaning it has a magnitude but no direction. Torque, on the other hand, is a vector quantity, meaning it has both magnitude and direction. This is why torque can have a negative or a positive value depending on the direction of rotation, but work can only have a positive value. Power is the amount of work done over time. It's expressed in units of watts, where 1 watt equals 1 joule per second, or in units of horsepower. Using the definition of work we saw earlier, power can also be written in terms of force, distance, and time. And since distance divided by time, d over t, is velocity, we can express power in terms of force and velocity. But electric motors produce torque rather than force, and they rotate with an angular velocity rather than linear velocity. So for electric motor applications, output power is found by multiplying the motor's rotational speed, or angular velocity, by its torque output at that speed. Note that here, angular velocity is expressed in radians per second. If the motor speed is given in rotations per minute, or RPM, be sure to convert this to the correct units of radians per second. Horsepower, the imperial unit used to measure power, was introduced in the 1780s by James Watt and Matthew Boulton. They defined 1 horsepower as 33,000 foot-pounds per minute. This converts to approximately 746 Newton meters per second. And since 1 Newton meter per second equals 1 joule per second, or 1 watt, we can say that 1 horsepower equals approximately 746 watts. Because the power rating of a motor is determined by its rated speed and torque production at that speed, motors that operate at constant speed and relatively constant torque, such as AC induction motors, often use output power as a key specification. However, output power isn't a very useful specification for motors that operate over a wide range of speeds and torque values, such as servos and stepper motors. For DC motors, the torque speed curve is relatively linear, so maximum output power occurs when the motor is operating at a point that corresponds to approximately 1/2 the stall torque and 1/2 the no-load speed. For more information on motors and other motion control topics, visit motioncontroltips.com or designworldonline.com. Thanks for watching.